Hello everyone, my name is Maz Barami from Wolfram Research. Today we will follow the 10th session of Andreas Lauschke, a senior mathematical programmer who has been using Wolfram technologies for over 26 years. He will use a building function from continued fraction theory to show just how immensely precise the Gregorian calendar is, and with that, leave the calendar topic. Handing over to you, Andreas. Thank you for your 10th session.
Yes, hello everybody. Welcome to my 10th session in this Twitch TV series. Thanks for the introduction, Mads. So today I bring the date, time, calendar subject to an end, and I've chosen the Gregorian calendar as a particular application of the usefulness of viewing a numerical approximation from the continued fraction perspective. It makes for an intriguing subject that combines math with calendar, and I think you'll be amazed to see just how precise the Gregorian calendar is. But before I jump into it, I address 4 questions that were asked on YouTube. Following the last session about calendar in the mathematical system, Martin Leuter asks 4 questions. So let me look at these first and address them. So, first question, when Christmas occupies a full weekend, will previous date of weekend skip 7 more days? So, to tell you the truth, I don't really understand exactly your question. I'm not sure what it means when Christmas occupies a full weekend. Now, your name sounds German, so perhaps you're thinking about it like the German Christmas holiday, where Christmas is the 24th, and then we have the 25th and 26th as the first holiday and the second holiday. If not, if you have Christmas on the 25th, like in the United States, I have that as the second case here. So I think the answer to your question is in these 3 code blocks. So if we evaluate it for Christmas is the 24th, then we have it obviously as a Friday. I've set it up for 2021 so that it matches that way. And the previous date, that's the weekend date, is then Sunday the 19th. If you say Christmas is on the 25th, then the day name is Saturday and the previous weekend day is also Sunday the 19th, just from the previous week. You probably don't mean this. You probably don't mean Sunday is Christmas. And then the previous weekend day is just the preceding day. From Sunday one before is Saturday the 25th. Right? So I don't quite understand what you mean with Christmas occupies a full weekend. But I think one of these 3 items here should answer your question. Next, you say 2.45 days are 2 days, 10 hours, 48 minutes. Why is there a second missing? And I think the answer is simply that there is a rounding error. When you use a real, 2.45 is internally a real in the mathematical system, then there's a round of error. If instead we are saying 245 over 100, then we are getting the 44 here. Here's your extra second that you're missing here in the 43. Okay, so it's just round of error. When it's not time critical, and you do have plenty of time and you are after precision, I recommend that you use the rationals. If you're after speed and you're not too much concerned about error accumulation or truncation errors, I recommend using the reals and early on in your code. Right? But here this is the reason for the missing second. This is rounding error. Next, you ask if I add more than one quantity, will it add them in the given order or will it sort the quantities? And for that, I've written a mini code here. I'm taking random integers between -10 and 10. I use 6 of them because I want to show you this for these 6 items: year, month, day, hour, minute, and second. Then I permute all these and I'm putting the time in front of them. And then I'm using date plus, and I just picked an arbitrary date here, and I map this over the permissions. And then I'm asking for the absolute time and take the union. So the idea here is that I want to try all these 720 permutations, right? It's 720 because we have 6 items here that we want to permute. So the number is 6 factorial, and that's 720. and then I map this date plus operation over these 720. And I want to show that this will give you back one number. And if you get one number, then it's clear that we are getting the same result no matter in which order we have them, right? And we get one result back. The permutations themselves, however, are 720, all of them, right? So you see that they're all different. Yeah. So here we have month year, here we have year month, here we have day year. So it's 720 in total with these random numbers in front of it, but they're not changing among every column that we have in this big table. So what we can now look at is that we map the state plus operation over these permutations, and the result length obviously then is also 720, and we take the unit and get one number back. So I think this proves that we can use them in any order. They will give us the same result back. Okay. And your last question, what happens when adding a month to January 31 and Feb 29 respectively? And here are the answers. If we pick January 1st of 2020, which is a leap year, we are getting March the 2nd. And if we add 1 month to February 29th in 2020, also a leap year, we get Sunday the 29th of March. Right? This is how this works, and I think it's pretty normal for years that are not leap years. I think you're asking because you're interested in a leap year. Okay, I think that answers your 4 questions. However, in the future, please use the community section for questions, right? Please make a note of this URL. Please ask them directly in the community. I cannot interact with you on YouTube, because the YouTube section is under the control of Wolfram Research. I couldn't even add an answer to that, right? So we have a separate community section for extended discussions. Okay, with that said, let's jump into the Gregorian calendar with continued fractions. So the short summary, very short summary. Pope Gregory XIII set up a commission to improve the Julian calendar, and it was introduced in 1582, but not adopted by all countries immediately. And the leap year rule that you're of course familiar with is every year that's exactly divisible by 4 is a leap year, except for years that are divisible by 100. But these centurial years are leap years if they are exactly divisible by 400. So for example, the year 1700, 1800, 1900 are not leap years, but the year 2000 is. And the accuracy of this is quite incredible. It improves the approximation of the Julian calendar by skipping 3 Julian leap days in every 400 years, giving an average of 365 and a little less than a quarter mean solar days. The error is about 1 day per 3,000 years. However, the Earth equinoxes and perihelia are not constant. So to new non-constant precession of the equinoxes and the movement of the perihelion, that's the point where Earth is closest to the Sun, the error itself is a variable, which means the Gregorian calendar implies an error actually closer to 1 day every 7,700 years. And that's substantially more accurate than the error of 1 day and 128 years of the Julian calendar. I give you a side note for more on the introduction of the Julian calendar and Caesar's decision to add 90 days to 46 BC, making it the longest year of all times. Please watch this very illuminating YouTube video that someone else has created there. You will understand a lot about what happened back then. The year 46 BC is actually the longest year in history because Caesar added 90 days to it. And another side note below that, given that the Julian calendar has an error of 1 day in 128 years and he added 90 days, it means he solved 90 times 128 years or 11,500 years of offness with just 1 decree that he issued, and think that's rather efficient, I believe. Okay, so please read the Wikipedia article for more details and a historical account of the Gregorian calendar. It's more than exciting than your usual bedtime thriller, I think, and here is the link. Okay, now we come to the continued fractions. We have various theorems that establish that the continued fractions are best approximations to any number and also later than any function that uses rational expressions, and here just think fractions, just think the rationals. You'll remember the long division and the Euclidean algorithm from 4th grade. You're already using continued fractions without knowing about them. So here's an example, right? You remember how this works. We try to get 169 into 584. Well, that only works 3 times. That is 3 times 169 is 507. That gives us the 3. But there's a remainder, 77, and we're now trying to see how we can squeeze that into the 169. Well, we can do it 2 times. 2 times 77 is 154, gives us a remainder of 15. That gives us the 2. And then how many times can we put the 15? That's the difference of these 2 into 77. Well, that's 5 times. That brings the 5 in this position. 5 times 15 is 75, we subtract, and so forth, right? You know how this goes. And this gives us the continued fraction expansion of this fraction 584 over 169. Okay, and I mentioned already at this point, this seems to be a very efficient number representation, right? We just need to store 3, 2, 5, 7, and 2, and that's it, right? That's 6 integers, 6 digits, that are rather small, below 10, or we just store it as this fraction. So contrast this to the numerical expression, right? If we look at the first 500 digits of this fraction in a decimal representation, we're getting a period of 78 digits, right? From this 455 to here, and then starts the next one, 455 to here, and so forth. So if you were to look at this with the simple /n or on a pocket calculator, you would never see that the number is periodic. You would never see that the number has 78 digits and the period, and so forth. So let's check the period of 78 digits. We take the period, we divide by an equal number of 9s at the 3, and we are getting indeed our fraction back. But look what this tells you, right? 78 digits. And to store this, you would have to store 78 digits plus the 3 plus the information that this number is actually a period, right? You need to store a lot of stuff just in memory storage, or need to do a lot of number explorations in order to really understand this number in the decimal representation. Whereas here it's much easier, just store the fraction or store these 6 digits. Okay, and the continued fractions find their greatest usefulness in approximation theory in calculus, which is normally not the most important domain of the data scientist, and that's why I won't do any continued fraction theory here. But it is an exciting area of calculus that, in my opinion, is entirely underrated. Okay, so for now, just trust me that the representation of the year's length with continued fractions will be illuminating. So in the kernel, we have several continued fraction functions directly at our fingertips. We have these 3, and I also add convergence and rationalize to that. So we have already 5 very useful functions directly geared towards continued fractions. So let's look at the convergence of this fraction that we have already looked at. And we see these 6 numbers here, just as we had these 6 numbers here in the continued fraction representation. So the convergence, they give us a list with the convergence corresponding to the continued fraction terms, right? These are the terms here. These 6 terms, and the convergence you can think of that we are cutting off, we're doing a truncation here after every step has been done. So we have 3, and after the 3 after the 3, I don't know, I have a scrolling problem. Here's the 3. And next we have the 2. And if we cut off after the 2, we're not going on yet with the 5. We're getting the next, that is a 7/2. And so forth, right? If we're going through all these steps, these 6 steps here, then we get these 6 convergents, and the last one is the fraction that we started with. And it terminates because we have a periodic fraction, and that means the continued fraction expansion terminates. It's a simple irrational number. The continued fraction expansion does not terminate for the irrational number. For the transcendentals, for the irrational numbers, this goes on forever. But for rationals, for fractions, there is a terminal representation here. So we only have a fixed length list. Okay, so let's do some math for the Gregorian calendar. 1 year is 365 days, 5 hours, 48 minutes, and 46 seconds. And keep in mind that this itself is an empirical number because this changes every year and it is measured, right? This means this is a measured number, not computed, it is measured. And then empirical numbers are based on observations which have errors themselves. So this number is an adopted value which we have to treat as exact, even though it is not exact and it's also not constant. So if we are dropping the integral component for the day, we have the following representation. I should learn to submit on the right line. We have 10,463 over 43,200, and as a decimal number, a little less than a quarter. But now let's look at the continued fraction convergence to this. So let's ask for the convergence of R. And here you see that we get these convergence and we see the last number equals this continued fraction expansion that we started with. Obviously, it's just a fraction, therefore the continued fraction approximation converges in the convergence function. So each of those is a solution to the calendar problem with increasing accuracy. The denominator gives the length of the cycle and the numerator gives the number of leap years per cycle. So from this we see we could have 365 days plus 0. We could have 365 days plus a quarter day. That is basically almost the calendar that we're using. We could also use 365 days plus 7/29 days and so forth until the last one. We arrive at 365 days plus, well, this fraction of 5 digits over 5 digits. Okay, so let's go back to the list. If we use 7/29 days, it would be more accurate than if we're using a quarter day here. But it would also be more complicated. And looking at all, we really have only 4 realistic options that we have here. We have 1 in 4, that is almost our Gregorian calendar, and we have an error of 11 minutes. 7/29 would reduce the error, 1 minute 11 seconds. 8/33 would also reduce it even further, down to 19 seconds. 8/33 is here in our list, 8/33. And 31/128, that's the Julian calendar, gives us an error of only 1 second. We have that here, 31/128. So the first option is the Julian calendar, 1 leap year every 4 years. About 1 day in 128 years, right? That's the 11 minutes here and 14 seconds, right? That's about 1 day in 128 years. The second option would be much more precise, but it's extremely unwieldy. Just who would like to use primes like 7 and 129? The third option, 8 leap years every 33 years, has been proposed by the Persian and Tajik scholar and poet Omar Khayyam, whatever that is pronounced. I have to admit I'm not a scholar of Farsi, in 1079. It seems it didn't make it either, because 8 and 33 are not convenient numbers. The fourth option now, well, it's getting more and more accurate, right? The further down we go in the list, the lower the error is. An error of 1 second is of no practical significance, and it has been proposed, for example, by the Russian astronomer Medler in 1865 from the beginning of the 20th century. It called for just one correction to the Gregorian calendar, jump 1 leap year every 128 years. And reminder, the Julian calendar has 32 leap years every 128 years. But it has never been enacted anywhere, so there is no pleasant roundoff. The accuracy is striking. The error in the Julian calendar is 1 day 128 years, and this method from Medler uses 32 leap years in 128 years, right? And the best convergent would be 31 leap year. So if 31 and 32 and 128 weren't such unpleasant numbers, the best solution would actually be a modified Julian calendar, right? Something Caesar could never have noticed because there were no continued fractions around there. Just make an exception to your calendar every 128 years. And the error is 1 second every 128 years. And please also note that the Gregorian calendar is not found among these 4 choices, and continued fractions were not known in the 16th century. Yet the Gregorian calendar is extremely precise. So how did they do it? So today we would proceed with the continued fractions and lean towards the ratio of the last row, 31, 128, right? That's how we would approach it now. But we would want to replace the numbers with something more convenient, a round number, and among the many choices we'd also try 400 years. And if 128 years contain 31 leap years, that's option 4, then how many are contained in 400 years? Well, in the kernel we can solve for that. So we're setting up the equation 31 over 128 equals x over 400. Let's solve it, and we're getting a number that is pretty close to 97. No surprise here. So we round this number and we get 97 leap years for every 400-year cycle. This is exactly the Gregorian calendar. Reminder, no leap year if divisible by 100, except if divisible by 400. And this rule gives us exactly 97 leap years per 400-year cycle. But the above would use knowledge of 31 over 128 and today's known year length, which back then they didn't have. So that would have been impossible for the Papal Commission, because back in the 16th century they didn't have the high accuracy of a year's length that we have today, and no continued fractions, so no knowledge of 31 over 128. Instead, the Commission used the astronomical tables compiled by the Academy of Toledo on the order of King Alphonse X, also called King Alphonse the Wise of Castile, who lived in the 13th century. The length of the year in those tables was 365 days, 5 hours, 49 minutes and 16 seconds. Note that this is about 25 seconds higher than what we are using today. And if we use this number, converted to continued fractions, gives us these convergents, right? So thus the Pope's Commission could not possibly have been aware of 31 over 128 by any method whatsoever. However, they could have been very satisfied with their work. It is very precise, because if we now choose the option 4 from the list, this time using the Academy of Toledo's table again, we still get 122 over 503. This would now be our 4th option. And I think that's really not too shabby. And I mean, it's clear that all these convergents go towards a number a little less than a quarter. Hence, we get something around 97 for the number of leap years if we use a 400-year cycle. So if we use 122 over 503, we're getting also a number pretty close to 97, but we are closer to it, right? This number is closer to 97 than this number. Okay, so again, we are at 97 and 400. So this is the ratio that we saw already today. I mean, they're all coming towards 97. So let's look at some more. If we use the year length of the Academy of Toledo table, then we are getting this list. And a couple of comments about this one. Number one, note that these convergents here move in an alternating manner. So if we start with 100, then this 96 is less than 100, but then the next one is also less than 100, but more than 96. The next one is is more than the 96.9696. But then the next one is above. This one is below the predecessor. This is above the predecessor. This is below the predecessor. And that is one of the characteristics of the convergence of continued fractions. And in the end, we are terminated here. And again, we have a periodic number. And let's create the same table using today's year length. And we get this table and we get similar behavior, all right? We start with 100. This number is below the predecessor. This is above the predecessor. This is below, above, below. And the last one is again a periodic number, right? So we get alternating convergence and we get the periodic number at the end. And yeah, I've summarized this quickly in a side note here. So we get 97 plus 154 for the Gregorian number, and we get 97 minus 13 over 108. This is this number here for what we could do today. So with a planning horizon of 400 years, skipping 3 leap years every 400 years, that's the first order of business. That's what we want to have in our quality approximations. And if we look at the error that the the Gregorian calendar had here, it is less than 2%. Quite remarkable, right? Because this number of here we represent as 97 plus 1 over 54. That would be the precise number. They used 97. That gives us less than 2% of a percent error. Okay? And I don't want to beat a dead horse. They were not known in the 16th century, and the result was formed by trial and error by the Commission. So here I give my personal opinion how this could have been accomplished by them. According to the Academy tables, the Julian year was longer than the true year by 10 minutes and 44 seconds. So that begs the question, how many years would it take to accumulate that error until one full day is reached? So here I'm dividing it then. We have 86,400 seconds in a day. We have an error of 10 minutes 44 seconds. So let's divide it by this. Convert it into years. We have 134.2 years. Okay, that means one would have to skip 1 leap year every 134 years. But that would be complicated. 134 is an unpleasant number. However, notice that in the mental horizon of 400, it's pretty close to 400 over 3, right? And there's the 3 again because we're skipping 3. We have 3 non-leap years for every leap year. So we come to the same conclusion. Skip 3 leap years every 400 years. And this is the Gregorian calendar without the use of continued fractions. So the beauty of all it is that a rule like 4 years, except when divisible by 100, except when divisible by 400, is incredibly easy even for common folk to understand. Everyone understands 400 and 400. You don't need to be a mathematician for that. And this simplicity of the rule with small denominator early on was important. The denominator is 4, right? That's why we have the leap year every 4 years. So we have simple numbers and a small denominator, 4. That's why this expansion is so beautiful. So it means that Pope Gregory effectively assumed that the year was 4 seconds shorter than what he thought, not us today. He knew his computation was off by 4 seconds because he used the Academy of Toledo tables, not what we are using today. So then let's do a comparison. If we are using the Academy of Toledo tables, which was assumed to be correct by Gregory, that makes it about 25 seconds longer, right? We use 49 minutes and then 16 seconds. And that gives us these convergence We've seen them before, right? You remember the 122 over 543. But if we use the average Gregorian, we get a different number. That is 12. You see there's the error of 4 seconds in it. And here we get a much shorter list. And we see 97 over 400 in the last element, right? Very short, very simple. This is the system we're using today. And these 4 seconds difference that we have here between the first and the second results in this difference in these convergence lists, right? We're ending right here after 97 over 400, only 4 terms in the list. Whereas with 4 seconds longer, we could in theory develop more precision, right? We have up to 5 digits here in the denominator. The list is much longer, but these 4 seconds were the error that the paper commission accepted to provide for a easier solution, 97 over 400. And if we are using today's number with 45 seconds, and some astronomers use 46 seconds, then we're getting these 2 convergent lists. They both go to 31 over 128. And if you use 46 seconds, then you get 2 extra terms. So the second list of convergence ends with 97 over 400, which means exactly that. 3 leap years in 400 years without error, right? The list ends at 97 over 400. There is no more error that we have afterwards, whereas the other ones go further. So for a modern version, note that we have continued fractions. The problem is that the length of the year itself is not clearly defined, and the Earth's rotation speed is also slowing down. So a very precise formula or method would only make sense for the long run, right? I mean, we seek precision for the sake of correctness in the very distant future. And that means thousands of years, which then would necessarily have to take into account the consequences of the slowdown of the Earth's rotation. And in thousands of years, who would give us credit, right? What's it worth? Earth will have passed through another ice age, so we're better off just adding a second to a year occasionally. And that's what is done in real life. So for reasons of convenience, the length of the years explicitly change from time to time. Usually 1 second is added. At the year change from 2016 to 2017, the last minute of the year got an extra second. What, wait a second, you ask? Exactly. We had to wait a second before we could get into 2017. The last second of 2017 wasn't 23:59:59, but 23:59:60. So I think this is wrong. This must be 2016. Sorry for that. And it wasn't the first time that did that. We've been adjusting the clock since 1972. And in 34 years, we've added 26 leap seconds to the year. And as the Earth's rotation slows down over time, we'll see the second adding business more frequently in the future. On the other hand, though, it also means that the Gregorian calendar becomes progressively more correct, however, at ridiculously slow speed, because the Academy of Toledo had the year's length some 27 seconds too long. And as the Earth's rotation slows down, eventually we will be there. And there is a nice Wikipedia page about this. Please have a look also at this page. You can clearly see that the last second of the year 2016 was 60 seconds. It's a nice page. It also shows you the difference between UT1 time and UTC time. You see that they apparently try to have a 0 in the middle of deviations that take about a second. And here's a table of the leap seconds to date. Started in 1972, and we're always adding 1 second occasionally. And you also get a chart of the Earth's rotation around the Earth, the errors of that. Okay, so that brings me at the end of my presentation. And I'm wondering if there are any questions. Thank you.